Okay, so I will continue with the Fourier transform of periodic signal. We know from the theory of Fourier analysis that any periodic function verifying the Dirichlet conditions can be expanded as an infinite sum k from minus infinity to plus infinity ck exponential jk omega 0 t, where omega 0 it is by definition 2 pi over t0, where the t0 is the fundamental period of the function ft. So we know also how can we determine the ck by an integration formula. So we don't need, for instance, this formulation, but here we are interested in getting the Fourier transform of this periodic function when its Fourier series is determined. We know that any constant k has a Fourier transform equal to 2 pi k delta of omega. So now ck is seen as a constant. If I will multiply a constant, a function which is a constant in k, by an exponential function jk omega 0 t, so I can use the property of the Fourier transform. Multiplication by an exponential in time results on a delay in the frequency domain. So ck has a Fourier transform equal to 2 pi ck delta of omega. If I will multiply it by an exponential function, I will get the Fourier transform evaluated at omega minus k omega 0. So this function for all possible values of k has a Fourier transform equal to 2 pi ck delta of omega minus k omega 0. Now, the Fourier transform of the sum will be the sum of the Fourier transforms. So I can write the Fourier transform of ft, noted capital F of omega, will be the sum of the Fourier transforms of each value of this function when k varies from minus infinity to plus infinity. All right, so this is the result that we can outline if we know the coefficient ck for all k from minus infinity to plus infinity of the periodic function ft whose fundamental period is equal to t0, we can write directly the Fourier transform to be the sum from minus infinity to plus infinity 2 pi ck delta of omega minus k omega 0. So this is one option. It means if the function is given by its Fourier series, we can evaluate its Fourier transform by this expression. How about now if the periodic function of period t0 is defined by its generating function gt? So as you are seeing here, we have a periodic signal existing from minus infinity to plus infinity. And we have a shape which is repeated from minus infinity to plus infinity, which is this gate function of amplitude A and of duration equal to t. So this is exactly the rect function of amplitude A. So I can write ft as a sum from minus infinity plus infinity of this gate function, okay, delayed by a coefficient that depends on k. So gt minus k t0, where k is varying from minus infinity to plus infinity. For k equal to 1, I will have gt minus t0, which is this part. 2 times t0, it will be this one. If I will reverse the k, okay, so the k, if the k is negative, so the g of t plus t0 will be this part. gt plus 2 times t0 will be that one. And when I make k varying from minus infinity to plus infinity, I will build my periodic function ft. So I use now the property of the convolution. So G evaluated at t minus k t0, when k varying from minus infinity to plus infinity, will be the sum of gt convolution of delta with delta t minus k t0. The Fourier transform of ft now, noted f of omega, will be equal to the product of the Fourier transform of gt, that we note g capital of omega, and the Fourier transform of the signal pt defined by the infinite sum of the delta of the pulse, the train of pulses existing from minus infinity to plus infinity. Right. We see that pt is a periodic function that we call here the train of pulses, which is existing from minus infinity to plus infinity. So we can calculate now the Fourier series of this train of pulses. So it will be sum minus infinity plus infinity ck exponential jk omega 0 t, where omega 0 is 2 pi divided by t0. ck will be 1 over the period t0, integration over 1 period of the pulse delta t. So this is the basic function dt. So if we will integrate, we will have 1 over t0. So we have the coefficient now ck to be constant for all possible k, which is equal to 1 over t0. So this is the train of pulses existing at discrete instant, multiple values of t0 with negative and positive sides. And f of omega will be 1 over t0, okay, will be 1 over t0, exponential jk omega 0 t. So the pulse gives also a pulse of amplitude equal to omega 0. So now the Fourier transform of the train of pulses, we will note it the capital P of omega, and it is equal to 2 pi over t0 delta of omega minus k omega 0. As a result, the Fourier transform of f of omega will be the product of g of omega times the p of omega, because we have a convolution product in the time domain. And here I will multiply, and we see that the g of omega is not dependent on k. So when I will multiply the j of omega by the delta of omega minus k of omega 0, so this delta function is existing only at k omega 0 and 0 otherwise, multiplied by g of omega gives g of k omega delta of omega minus k of omega 0 times 2 pi over t0, which is by definition omega 0. So this is another possibility, is how can we express the Fourier transform of a periodic function when it is defined by its generating function gt, which is a basic function which is repeated from minus infinity to plus infinity. So here we are, I am summarizing in this table the most important function that we are accustomed to see when we solve linear time ordinary differential equations. We see the sine, the cos, exponential function, and other functions that we can compose from those basic functions. Of course, we start with the definition, the inverse Fourier transform, the Dirac function, the delayed Dirac function, the step function, the constant, the sine function, the exponential, the sine and the cos, and the rectangular or the gate function of a duration equal to t. And the cos of omega 0 t when time is positive. And here I am summarizing the Fourier transform, the properties of the Fourier transform, the linearity, delay in time, time reversal, time scaling, time transformation, duality, frequency shifting by multiplication by an exponential in time, the convolution products, which is a basic operation that are seen always in the study, in the analysis of linear time invariant systems, the modulation or the multiplication of two functions. And here we see the duality between the two properties, the integration, the differentiation, multiplication by a polynomial function of time. And this is it is a relation which says that ft, if ft is real, then f of omega is equal to f star of omega, which is the complex conjugate of f. For instance, we have arrived to those relations, which is a periodic, the Fourier transform of periodic functions defined by its Fourier series, all defined by its generating functions. So here pay attention, there is a k, the n should be replaced by k, so there is a typo error here. So we have j of k of omega 0 times this expression. So I will focus now on the energy, spectral density, the signal energy, signal power, and the relations between them in my next videos. I will invite you also to see the other videos where I am solving some problems of Fourier transforms, and how can we use the properties of the Fourier transform in order to get the solution in an easy manner. Okay, so I invite all the students to see the next videos related to examples and solved problem of Fourier transform.